Okay. Oh, time to get going on a lesson, so gotta turn off the music. Sorry. Anyhow, 2.4. So today we're going to practice looking at some postulates, and to increase our understanding, we're going to draw some pictures of those postulates, and that's pretty much what we're doing today. Is just practice visualizing things. So we'll use diagrams, and we'll try to understand postulates using diagrams. So our objective today, students will be able to identify postulates illustrated by diagrams. We'll also practice drawing the diagrams from a postulate. So not too bad. Let's go. So these are some of the postulates we've already had. We've had the ruler postulate, segment addition, protractor postulate, angle addition, and so those are ones that you should know already. But what we're going to do is get about 6 more of them today, I think, something like that. So here's the first one, a point, line, and plane postulates. So postulate number 5 says through any 2 points there's exactly one line. For any 2 points. So what you might want to do is try to draw that. And so if we have any 2 points, like let's say we have a point right here, and then we have another point over here. What we're saying is that, I'm going to try and get this on here right. What we're saying is that, wow, that's awful. We're going to say that there's, let's do it this way. Okay, so imagine those points were drawn already, and imagine they were right here and right here. So there's point A and B. So through any 2 points there's exactly one line. So what it's trying to say is that you can't have a second line that also passes through the points. Like, for example, you might say, well, what about this? Okay. There you go. A second line. Well, actually this blue thing that I've drawn is not a line, because we found out before when we're setting lines that lines are perfectly straight. So this blue thing is more like a curve. So what it's saying though is that you can't have more than one line that passes through points. That passes through these 2 points. So and try not to be too crazy about this. Remember, points are really, really small. In fact, they have no dimension, and lines are made up of a bunch of points stacked next to each other. So they're actually really thin. In reality, in practice we draw these lines like this, but reality, as far as geometry is concerned, lines are really, really, really thin. So you can only get one line through 2 points. Okay, so there's a little picture of that last one. Here's the second one. Postulate 6. A line contains at least 2 points. Well, this one seems kind of dumb because, well, in my opinion, it seems kind of dumb because a line actually has a whole bunch of points. I mean, if you think of it going like this, a line going that way, a line going that way, how many points does it have? Well, there's one there, there's one right here, there's one right here, one right here. And so a line contains at least 2 points though. And so what this postulate is saying is that you cannot determine a line based on a single point. Let's see what happens when you do that. If you have a single point here, then we don't know where the line is. The line could come from this direction and pass through that point. Okay. I have another line coming this way. Alright, pass through that same point. This is a big point now. We have another line going this way, another line going this way. So to determine a line, we need at least 2 points, because once we add on this second point, like a point here and a point here, then we know we're talking about this line right here and not those other lines, you see. And so that's what basically this postulate's saying, is that a line contains at least 2 points. Well, in reality it has an infinite number of points, but you can't have less than 2 points to determine a line. So, I don't know. Hopefully that makes sense. If two lines intersect, their intersection is exactly 1 point. Well, can you draw a picture of that? Well, sure, there's one line here, and here's another line here. And their intersection is just this single point right there. And again, someone might try and say, well, what about this scenario? There's a point here and a point here, and if I draw a line going like this and like that, it looks like to me they intersect in 2 points. Well, once again, this thing that's on top here is not a line, because lines are straight, and so we can't have this scenario. So that doesn't come up. So postulate 7 says if two lines intersect, their intersection is exactly 1 point. And so keep in mind, you can't fit in a point here and a point here and fit them both in, or even 3 points or 4 points. This postulate is saying that there's exactly 1. So, that in mind, we only have 1 point as far as the intersection. Only 1 point. Okay, well that's straightforward. Through any 3 non-collinear points, there's exactly 1 plane. Okay, so one key thing on this one is this non-collinear point idea. And that means the 3 points have to be not on the same line. So you have 2 of the points be on the same line. I mean, there's a single line that would go through there, but the third point has to be somewhere else, not on that line, say like over here. And now we can draw a plane kind of going this way that has those 3 points in it. You see? Oh, that's ugly. Okay, so once again, the point is, if I have 3 points that are collinear, let's take this word non off here. Any 3 collinear points, well, that creates a problem, because there won't be, I mean, let's put the 3 points up here. That's all 3 on the same line. Well, there's a plane that goes that way. Okay. And here's another plane that kind of goes at a different angle, and it passes through those 3 points also. You can see this sort of makes an angle here. This isn't the best drawing here, but let me try to improve it a little bit. You can have this scenario here where there's like an angle between the 2 planes. The plane kind of going underneath here. So this plane's kind of going straight up and down, and this one's going at some angle cutting. But they both pass through these 3 points. And you might imagine that, well, you can draw another plane in between these 2 right here, you know, that would go through also. And see, so there's a whole bunch of planes that could pass through those exact same 3 points. So that is why we say, once again, the 3 points have to be non-collinear, because once you state that, there's, okay, well, there's 2 points, but if you put the third point on this plane over here, then you know that you're talking about that first plane, and you're not talking about these other 2 planes. Okay. On the other hand, if you put the point over here on this one, then you know you're talking about this plane. So that's going vertical. So That's the whole reason why we have this word non-collinear in here. And once we do that, we say that there's only one plane possible. Okay, and so once again, planes can't curve, so planes are flat. So you can't have this scenario. Whoops, back that up. So you can't have this scenario where you have one plane here that passes through the three non-collinear points, and then have another plane that kind of folds around this way and passes through those same 3 points. Okay, this is kind of awful looking, but in other words, you can't have a curved plane. In our class in geometry, we only have flat planes that are straight, and they're only in 2 dimensions, so you can't have that scenario. Well, a plane contains at least 3 non-collinear points. So again, obviously a plane has more than 3, but it has at least 3. You can't have a plane with just 2 points because we wouldn't know where the thing is. If there's only 2 points like this, you can draw a line through there, and we found out that if the points are collinear, from the discussion on this postulate, if the points are collinear, you could have multiple planes. You could have various planes coming through at all different angles, and they'd all pass through those same 2 points. So we have to have at least 3, and once again, they need to be non-collinear. So anyhow, postulate number 10: if 2 points lie in a plane, then the line containing them lies in the plane. Let's draw a quick picture of that. What this one is saying is that if you have a plane, okay, there's a generic plane, and you have 2 points that are in the plane, then what it's saying is that the line that contains those 2 points, and I'll try to draw a line. Okay, that's not too bad. The line, the entire line is inside the plane. Now, it looks like I've drawn this so that it goes, oh, it looks like it escaped. The line didn't escape, and why is that? Well, the reason why is because the plane actually goes on forever in that direction, and the plane goes on forever in this direction, and the plane goes on forever in that direction, and it goes on forever in that direction. So the bottom line is, if part of the line is in the plane, well, then the entire line is in the plane. And that's what this postulate's saying. Alright, so I think this is the last postulate for the day. We got 1, 2, 3, 4, 5, 6, 7 new ones. If 2 planes intersect, their intersection is a line. Okay, so you might remember when 2 lines intersect, you get a single point. But when two planes intersect, their intersection is a line. I'd like to draw one real quick. Let's try. There's a plane going right here, generic plane, kind of going like that. And let's just think of another one here. I'll draw a different color now. Green. There's a kind of a vertical plane coming, kind of going this way, and continues down underneath like this, and it's kind of going. So this plane's kind of going vertical, and this plane here is kind of, it looks like it's passing through right here, kind of like that. But that's where the 2 planes intersect, and it almost looks like there's a segment here. And so you might say, well, the intersection is a segment. Look, there's a segment right there. Well, But that would be false. And why is it false? Well, because this black plane actually goes on forever that way, and it goes on forever that way. And so that means this green intersection between the two planes goes on forever that way and continues to go through that way. So actually we get the entire line, you know, goes through here. And so that's what postulate 11 is saying. If two planes intersect, then their intersection is a line. There's the line right there. Okay, so I've kind of made drawings for you already, so you have an idea how these all work. Now let's try some of the questions. Okay, so one way to graph a linear equation is to plot 2 points whose coordinates satisfy the equation and then connect them with a line. Postulate 5 guarantees that there is exactly one line. A familiar way to find common solution to linear equations is to graph the lines and find the coordinates of the intersection. This process was guaranteed by postulate 7. Okay, so this little note just referring to algebra, you might remember when we're graphing equations of lines like say 2x plus 5, what they're saying is that, you know, all you need to do is make a t-bar where you do your x's and y's, you know, and all it's saying is all you need to do is plot 2 points. So you might have a point here like at 5, and you might have a point over here, you know, that's right here, and all you need to do is plot those 2 points, and then you can draw the line through those 2 points. Well, what we're saying here on this little paragraph here is that's the reason why. It's postulate number 5 that says that. It says there's exactly one line. So you can have any 2 points and there's exactly one line through it. And you remember from algebra that there is only one line. Well, the same is true for the second part here. It's saying, remember from algebra, you might remember again that if you have a coordinate plane here and you had maybe one line coming across here and you might have had a second line coming across this way, well, the place where they intersect is what they call your solution. Okay, solution. Okay, and you might remember that from algebra as well. Well, in geometry class, we're just saying the reason why this happens is postulate number 7, which says the intersection of two lines is a single point. So, you know, we're just reading that and trying to understand what it says. So now we're going to practice with the diagrams, and what we want to do is we want to look at this diagram and figure out which postulate is being stated here. Now remember when you're reading this that this is your hypothesis, this will be the conclusion. Okay, so you're looking for a postulate that says if two lines intersect, then their intersection is a single point. Well, if we go back now a few slides, let's find out which postulate said that. I'll go back here. The intersection of two lines, then it looks like postulate number 7. Two lines intersect, then the intersection is exactly one point. So now we go forward, and what we do is we write down which postulate. Well, we say postulate number 7. Okay. What about this one? This one says if two planes intersect, then the intersection of those two planes is a line. So once again, you go back, and by the way, these postulates are all on your book, so they're all on a certain page. I took the slide that I made right here is from your book. So two planes intersect, we want to have exactly a line. It looks like it to me it's postulate number 11. If two planes intersect, the intersection is line. So now I go back here and we answer this question. Well, which postulate is this one? This one is postulate 11. And we can just abbreviate postulate number 11. So you're going to have some problems on your study guide, some problems on your assignment where they give you the diagram and you got to figure out which postulate is being illustrated. Ah, we're right. Okay, so let's continue. I see. So use the diagram to write examples of postulate 9 and 10. What the heck does that mean? Okay, so let's take a look. Postulates 9 and 10. What did postulate 9 and 10 say? Well, let's go back and see what 9 said. Okay, so let's see if I can go back and look at postulate 9 and 10. Okay, so 9 said a plane contains at least 3 non-collinear points. Okay, so let's read that again. A plane contains at least 3 non-collinear points. Okay, so let's go forward then and see if I can go to that. Forward. Okay, so we need to pick a plane here. So anyhow, what it says, like if we talk about plane, well, there's this plane P here, this plane that's kind of going sideways. It has 3 non-collinear points, B, A, and C. So what we want to do is basically an example of postulate. We can say plane P, okay, plane P is determined by, by the points A, B, and C. Now, one thing we know about those 3 points is that they're non-collinear, so should probably add that in. Okay, so plane P is determined by the points A, B, and C. Okay, so that's what I think we're supposed to do for number 9. What was number 10 now? Let's go back and read what postulate 10 said. Okay, now, so the number 10 says if 2 points lie in a plane, then the line containing them lies in the plane. Okay, so now we need to kind of state that in terms of this diagram, I guess. If 2 points lie in a plane, then okay. Let's go back to that spot. Where were we? Okay, so here's, we could talk about this plane P again. That's this plane going sideways. There's 2 points in that plane, A and B, and there's a line that goes through them. So what we want to say here, since A and B are contained in plane that's supposed to be a capital script letter, but I don't know how to write a capital script letter. So in plane P, the entire line line AB is also contained in plane P. So that's basically what theorem or postulate 10 was saying. So anyhow, what we're doing in this whole lesson is basically working with diagrams, trying to write out what the postulates say and vice versa. So let's see here. Did we have this right? Plane P contains at least 3 non-collinear points, A, B, and C. Point A and B lie in the plane P. So the line, yeah, that's what we said. So we get the idea. Alright, so one thing we have to watch out for when we're making diagrams is making assumptions. And that's what this whole problem is about. So let's take a look at what you can assume and what you can't assume. So let's just go over these step by step. All points are shown are coplanar. Well, all these points are drawn inside the plane, so the way you get a point that would be non-coplanar is maybe draw a point up here. Now you think the point, I'll just call it Z. Point Z is like floating above this plane. So if you draw boundaries on a plane like this and then you draw a bunch of points inside there, we can assume that they're all coplanar. In other words, they all lie in the plane. Now, can we assume, let's see, AHB and BHD are a linear pair? Well, since this is a line, okay, right here, and AHB is this angle here, okay, and BHD is here, we can assume that we have a linear pair because this is a line, and these are intersecting lines. And those two angles are adjacent, so we get a linear pair. Okay, what else can we assume? AHF and BHD are vertical angles. Well, those are two lines that intersect, so naturally you got vertical angles here and here, and you also have vertical angles over here and here. So it's okay to assume that. AH, J, and D are collinear. Oh, AH, which is that point right there, and J and D. Well, those are all on the same line, so that's okay to assume that they're all collinear. AD and BH intersect at the point H. Okay, so I think that's pretty straightforward. Those are things that we can assume. Now let's take a look. This might be more interesting. What are the ones that we cannot assume? Okay. What we cannot assume is that G, F, and E. Now, it may look like you can draw a single line through there, but since no line is drawn through there in the diagram, we don't know for sure. I mean, I'll try to draw this. I mean, the point is, since there's no line drawn in here, that line could be off by just a little bit. Okay? And since lines are really, really thin, all it needs to do is miss that line by just a little bit, or miss one of those points. And I don't know, I've drawn this pretty bad, but you can see in that case it would miss point E there, and it just needs to miss it by a small degree. So if no line is drawn in the diagram connecting those three together, you cannot assume that they're collinear. Okay, clear enough. BF and CE intersect. Oh, that's interesting. Okay, so even though the planes go on forever, you might assume that since they're both in the plane that, well, you know, it looks like to me it eventually go clear over here, and this one would continue over here, and it eventually intersect. Well, that's what they're saying, is that we cannot assume that. We cannot assume that they intersect. It may have turned out that these two lines are actually parallel. They might be parallel to each other. So it may be that they never intersect. So again, they're saying that we cannot assume, and you have to avoid the habit, well, it looks like they would. Well, things might not be entirely accurate, or the diagram might be a little bit deceptive. But the point is, if we make a diagram like this and we don't draw that the lines have intersected, we cannot assume that. Cannot assume that. Oh, what else? BF and CE do not intersect. Okay, BF. Oh, so that's another thing. It's saying the opposite here. It says, likewise, we cannot assume that they don't intersect. I mean, because they might intersect. So this is kind of interesting. It sounds like they're contradicting. But the point is, you're not sure because there's not more markings on the... I mean, if there were more markings on the diagram, like I said, if there were their parallel symbols, if you had parallel symbols on the lines, then you'd know that they don't intersect. But what this is saying is, since there aren't any marks on the diagram, you cannot assume that they're parallel or not parallel. So that's kind of interesting. Make sure we're careful there about what we consider in the diagram. Okay, how about this one? Angle BHA and CJA. BHJ, that's this angle over here, and CJ. Okay, so they're saying we cannot assume that they are congruent. Okay, so there are some marks missing here. If we knew that these lines were parallel, then it would turn out that this angle here is congruent to this angle here. But again, we don't know that the lines are parallel. Since the lines are not necessarily parallel, we don't know that those two angles are congruent. We want to avoid the situation where we say, well, it looks like they are. Well, in geometry, we want to be a little bit stronger with our statements. And we want to be able to prove that they are, if indeed they are. Okay, how about this one? AD and BF, or, oh, AD is perpendicular to BF. And the measure of AHB. Well, you'll notice that in the diagram, they didn't draw a right angle thing in there. Since that wasn't drawn in the diagram, we cannot assume that they're perpendicular or that they're 90 degrees. So this whole slide is just helping us realize what we can assume and what we cannot assume. And so we have to be careful. Alright, well, let's try a problem where we have a description and then we need to draw a picture that has that description. So sketch a diagram, TV intersecting PQ at a point W so that PW is congruent to VW. Now, I have to admit, these are kind of hard because you almost got to come up with the diagram in your head, but what I would recommend is just start drawing things that you do know. Okay, so for example, we start off with a line TV. So just draw a line TV. Okay, well, TV has to have 2 points on it, so just draw in 2 points. So we at least know that information. Okay, so now there has to be another segment in here that intersects PQ. Okay, so where is PQ? Well, again, you can just draw a generic segment. Let's put in a segment. Try it right here. We'll just try something and see what happens. So if I put P here and I put Q here, there's a segment and says the point at the intersection, this point here would have to be W. So it says a sketch TV intersecting PQ at the point W. Now what we want is TW to be equal to TW to equal, we want that segment to be congruent to VW. Obviously my diagram's wrong, but what I need to do is maybe put V over here, and then they'd be equal distance. So let me just fix this now. I have an idea how to fix it. So start off with that again. I'll put T here. There's my line. And I'll put V over here. And I can once again have this, but let's put this near the middle like that. And here's my segment P and Q. Now I'll call this point right here W. And now you can see that this segment would be equal to this one. That's what we're trying to do. You see, so anyhow, when you have problems like this, just tinker with it. Just do what you can do and then make corrections to it. So I went from this diagram to this one. And now this is the correct picture for that scenario. TW is congruent to WV. Alright, so not too hard. Sometimes there's multiple answers that would work. Alright, so now we're going to read about perpendicular figures. Okay, so perpendicular, it's a line is perpendicular to a plane if and only if the line intersects a plane and a point and is perpendicular to every line in that plane that intersects it at that point. In a diagram, a line is perpendicular to a plane must be marked with a right angle symbol. Okay, that seems pretty straightforward. So the point is, if I drew another line through that passes through that point, it would automatically be perpendicular to this one. So let me see if I can draw another, you know, hey, I got pretty good. If I put another line here, it would also be perpendicular to that point, to this line T here. So basically it's saying if you have a line that's perpendicular to another line and it's in a plane and it passes through that point there, it's basically saying it's perpendicular to every line that intersects that point. So you know, you could even have another line that came in and that passed through that point. We can think of this point right here. Let me see if I can get another line going this way. Well, there's another one that's going to be perpendicular. So alright, anyhow, might use that idea a little bit later on. Alright, so let's practice a little bit with our diagrams. Let's figure out if they can be assumed or not assumed. Okay, so A, B, and F are collinear. Well, if there's a line that's drawn through all three of those, then we could assume that's true. So it looks like A is here, B's here, and F's there. There's a line that's drawn through all three of those, so we can assume. So we're going to say can. How about E, B, and D? E is over here, B and D. Now it may turn out that there is a line, but since no line is drawn in the diagram, we cannot assume this one. So we're going to say cannot. Alright, how about AB? Segment AB is perpendicular to plane S. Well, that right angle symbol is drawn, and we had a theorem earlier that says if you have the right angles, then that means that lines and planes would be perpendicular. So since that's drawn in the diagram, we can assume that one. That's okay. How about plane CD? Plane CD. Oh, excuse me. segment CD. Okay, so now is perpendicular to plane T. Well, this line on the other hand might not be. Notice that there's no right angle drawn over here. Since there's no right angle drawn there, you see, we cannot assume that segment CD is perpendicular to T. So cannot. Alright, how about this last one? AF intersects BC at the point B. Okay, so there's BC and there's this line AF, and that point is drawn right there, and that is point B. That is drawn on the diagram, so we can assume that. Alright, so that's not too bad. Hopefully we got it right. Alright, so finally we're up to the essential question and a little summary here. How can you identify postulates illustrated by a diagram? You can identify postulates from a diagram by determining which information you can assume. Do not assume congruence, midpoints, and bisectors. Determine which postulate applies, and so on and so forth. So that kind of concludes this lesson. So